Therefore, the question comes, are we planetary? This question was first put forward by Isaac Newton and people who followed him immediately after. Even the orbit of the Earth should be stable. The reason is that we have here the Sun, and here's the Earth going around it. You all know that the two-body problem is stable. There's a circular orbit or slightly elliptic orbit. But as soon as you put another planet, let's say Venus, then Venus will have a pull on the Earth. Every time they pass each other, they will pull, and you could imagine that after many, many revolutions, Venus will just pull Earth out of the orbit and we will fly off somewhere to cold space, or we would fly into the Sun. And this was a very real question in the 18th century, because we thought that the Earth was about 6,000 years old. We had only had about 6,000 revolutions, and at any revolution now we might just fly off. So it was one of the prime questions of the science of that time, to decide whether the Earth's orbit was stable or not. So let's see how we would go about it, and I'll take a slightly more general approach, namely it comes to a three-body problem. So let's say that we have here two bodies going around each other, and here's a third body going a little further away. So what you can say now that in the first approximation, this third body goes around the center of mass, the binary. But that's not quite true, because this third body is attracted by these two bodies separated, not on the center of mass, and therefore you don't really have the elliptic orbit. So you have some difference. The first approximation, you have a difference, which is the difference between the true force and the imagined force on the center of mass. And the difference is what is called perturbing force. So then you can do a calculation where you say that you have a perturbing force of certain magnitude f, which is thus the difference, and then you have a certain velocity, and you calculate the energy change in the orbit, which is thus the integral of f of v. The usual way to calculate the change of energy, and then after one orbit you find that maybe you don't come back to this orbit, you might have another orbit, and after another revolution might be another orbit. So you have to solve this problem, and it's not an easy problem. You can do it if you know the techniques in about 20 pages or so. It was done first by Laplace in late 18th century. And his answer was that to the first order, if you just take the first order correction, you can only do this correction, the difference force, in series. If you only take the first term from the series, there's no change in the semi-major axis. The orbit is stable. About 100 years later, Poincaré showed that even if you take the second order term, it's still stable. And this is the reason why our Earth has a stable orbit. It's not because we follow a Keplerian orbit, but it's because these perturbing forces integrated over the whole orbit give you zero. That's the real reason. And that's why planetary systems are stable. Now, the next question is, and that's something that has come up more recently, is that if we had another star, of course this was quite a heavy body, here's our Sun and the Earth, would that still apply? Well, the theory should apply because it's a very general theory. So we would expect that even if you put a star here, the planetary system should still be stable. Now, as it has turned out, now that we are able to do these integrations of orbits, actually calculate the orbits very accurately, we can bypass going through these long series expansions and complicated calculations. It's really type of calculations that took years and years from the experts in the 19th century. And we can do it more accurately, faster. So let's see what has been done in this situation. First of all, there have been some work already in 1930s and then again in 1960s on the effects of passing stars on our solar systems and planets, and that was obviously something we should think about. And again, you find some results about the stability. And then there was some numerical integrations when that became possible in 1970s on the effect of a companion star. But these were done with a low order accuracy and also rather few orbits. The results were somewhat inconclusive. So how you look at this now, if you want to give some criterion for stability, what is really important is how close does your companion star come to the orbit of the planet. So you measure this closest approach distance q in relation to the size of the planetary orbit. And usually you ask what is the closest you can come without disturbing the planet. What is the value of q? Well, Harrington gave a number 5, and that's what people usually use. But actually,
what is the mass ratio which they expect in person?
Well, this would be a general case, so it could be any mass ratio. So what we did some years ago is in our group we have here rather accurate integration methods, mostly due to Seppo-Mikkola. We did look into the situation of having a star perturb our own solar system. Just took 4 planets, the 4 bigger planets, major planets, Jupiter, Saturn, Uranus and Neptune, and asked what would happen to that system if we actually have a solar companion star. Well, we probably don't, but it would illuminate what would happen in some other system. So the result turned out to be very interesting. What we found that even though we knew from all this classical work that this planet should be stable, well, it wasn't. What happened that the planet would just dive into the sun? Well, that wasn't very reassuring. It looked like it might be in danger, especially if you have a companion that we haven't discovered yet. And of course, we're very excited we have discovered something very new until one of our colleagues was able to tell us that it's Kozai mechanism. That is, a Japanese astronomer called Kozai has discovered this in 1962. It's just that it wasn't well known because he applied it to the orbits of asteroids and comets in the solar system. And also, his work is not easy to read. In fact, nowadays I've seen people referring to Kozai and they're saying, read it from Innarin and Tal because you can understand it that way. So anyway, we learned something new there first ourselves and then discovered that it wasn't so new. Now in those days we did not know of any planetary system yet in a binary star, but one was discovered just during this work. So of course we got in a great hurry to finish it. But unfortunately our main author had talked about this to his colleagues who rushed and wrote a paper in Nature just before us. So they got all the publicity out of this. But anyway, I think we did a much more thorough job because we had more time. Okay, so let me just go back to the basic theory. We have this perturbing function, which this is some function that tells you the difference between the elliptic orbit and the real orbit in the first approximation. And the actual force, perturbing force at any time, depends on this angle, how the different systems are about to lie. The perturbing function looks like this. The polynomial that is used, the series is in Legendre polynomials, and take the first term. And then there are standard methods from there. You can do averaging. You average, because you're not really interested in what happens at every minute on this orbit, but you want to know what happened after this has gone around at least once and this has gone around once. This is the result, and then you do averaging, and this is a somewhat tedious process, but you come up with, which is a very simple formula for celestial mechanics. Includes the eccentricity E of the orbit, includes something that's related to the orientation and the inclination of the orbital planes, the same major axis of the inner orbit, and the outer orbit here is described by the semi-minor axis. The mass of the star comes in up there, of course. Once you have this, then there are standard methods in celestial mechanics, the so-called Lagrangian equations of motion, which again used to be standard for all astronomers, but nowadays no astronomers seem to know it except a few. But anyway, if you do that, it's a very simple step to write the equations of motion for the change of various orbital elements, inclination, eccentricity, and these orientation elements. The time unit here is this evolutionary time. You can see that that time unit depends on the semi-major axis of your planet. So you have the same equation for every planet, except that you have a different time scale. Every planet has their own time scale. So you really need to do this for one planet, and you should know the true answer. Actually, it turns out not to be so. Okay, so we're mostly interested in this eccentricity because we found that even though the same major axis doesn't change, the eccentricity does change if it has any value which is not zero to start with. It's proportional to the initial value, but if it's something else, then it will grow. And in fact, you can get the first order solution to that equation, time derivative. This function like this that depends on the initial inclination. You can see that it goes to zero at value of sine pi 0 square root 2 over 5. That is inclination greater than about 39 degrees, the eccentricity will change. And now calculating numerical orbits, we see that that really happens. Start with very small inclination, like eccentricity 10 to minus 6, almost circular orbit, and you can see grows all the way to almost 1 with the inclination 85 degrees. And if you put 90 degrees, you'll find that the planet will just go straight into the sun, and that's the end of us. So, well, since that hasn't happened, we know that we don't have such a planet near to us, but that certainly would put a limit to what can exist in some other systems. Now, interesting thing is also that the increase of eccentricity does not depend on how close this companion is. It could be anywhere. The scale doesn't come in anywhere except in a time scale. So if you have a companion very far away, it just means that you will dive into the sun later. If it's closer, you dive sooner. So if there's nothing else in this universe but our sun and this star and our planet, you'll dive into the sun sooner or later. And here now, what I have calculations for one specific case. We have inclination 80 degrees, that is, the companion is rather perpendicular to the plane of the solar system. Companion mass 0.1, solar mass is probably hide a black hole of this mass. At 400 AU, it's 10 times the distance compared with Pluto's distance. And in this integration, we can see that here the eccentricities, putting the real eccentricities of the planets, they start to go up and down and up and down. Finally, we lose Neptune here. Eccentricity goes to 1 and Neptune goes to the Sun. So this was an unstable system. What happened to the inclination? Same kind of thing. It goes, inclinations now 80 degrees is our basic plane, goes up and down quite a long time. The node, that is the line that tells the orientation of the two planes. That changes very steadily for all planets. Here it has a 360 degree jump, so it just keeps on going very steadily for millions of years. You can see here 100 million years. Just keep going, and they all go together. And this was a surprise, because what I told you in the beginning was that each planet has its own time scale in a three-body problem. Now they all go together. That's something that hasn't been explained. That's just an experimental fact. But the planets are tied together. It's not a collection of bodies each going around the sun. They know about each other, hold on to each other, keep the same plane. So you can't really tell whether it's a companion from the fact that the planets are in the plane. They want to stay together. If you remove the force between the planets, then that glue disappears. Here's a run where we just artificially took away the force between planets themselves, and you can see each planet starts to do its own thing. They go like you would expect from the theory, but the true orbits here, they stay together in this same line. Solar system plane. So then you could ask what are the conditions for stability, and calculate the number of cases, various inclinations for the companion, various companion masses, all at the same distance, 400 AU. And then we found that, first of all these with low inclinations, they are always stable. But with high inclinations, you start getting unstable ones here with higher companions. And now you can apply this to any scale by just remembering that there's a time scale. There's a factor V2 the third, that is the size of the outer orbit over the mass of the outer orbit here of the companion star. So you can scale these to any other system you like. The stability depends on this parameter, but it also depends on inclination. And the surprising thing was that we found in this work was that it depends on the internal dynamics of the planetary system. Now I think what we think that is happening that since the planets also perturb each other, if the planetary perturbations are greater than the perturbations from the outer star, then the planetary perturbations are stronger, and that makes them go together. So the planetary system is rigid, and you can tilt it, but they all go together. And the system that was discovered while doing this work is called 16 Sinus B. And then there are these other papers people Rust published right away. Okay, now you might still ask what happens here, because if you have a low inclination, it looks like everything is stable. You could never destabilize the system, but that can't be really true, because if you come close enough, you must be able to do something here too. So what I've been doing more recently is looking into even more general theory, and I'll just give you an answer. Okay, this is one calculation. Here the stability limit is the same Q that I told you that was thought to be 5 from the very old work. This Q here, how close you can come relative to the size of the planetary orbit. So here's quite a general formula. There's a mass of the star, and V is the mass of your central star, plus the planet. The planet is not important. E eccentricity of the outer orbit, EI eccentricity of the inner orbit, which is more or less 0 for planets usually. Inclination of the outer orbit. And then you have this some factor which is not 5, which is actually smaller. Now this particular formula guarantees stability for 10 to the 5 periods. That is 100,000 years only. If you want stability for longer time, then you have to put a bigger factor here. And in fact, what this work shows, you have to first tell me how many periods you want it to be stable, and then I can give you the factor. So there's no single number that you have to. It all depends on how long you want it to be stable. Well, what happens here is that you actually get something like a random walk. This planet is sort of kicked around in and out a little bit while the star goes around. It's a kind of random walk process, and after long enough time of these kicks, it is thrown out. So that's the end of your stable life as a planet. And just to show you that how this theory works, I have this numerical experiments and comparing this Q with inner eccentricities and experimental numbers, order integrations relative to the outer eccentricity. You have two groups, there's Arset and Marlin, higher numbers. The other one is Worm and Immonen. Now they got the very different numbers, and I think we can quite know why, but it's just because they set a different number of revolutions. The stability criteria was different, but if you take account what they use as their criteria, you get good fit to both. And here as a function of inclination, we can go much closer to the planet if we have retrograde orbit. Have to stay further out with the direct orbit. Experimental points from my favorite form. And I think that is about it. Thank you.
Okay, any questions or comments? Anya?
I don't know, what is the distance between the electron the virus
Okay, well, let me just, In this calculation, C roughly we have 0.1 solar mass star, and it's a kind of stable already for most inclinations at 400 AU. So it's still very close, but it's not a close binary system, wide binary.
What was the role of Finnish mathematician Sundman in this history?
He was dealing with the general problem, which where you have more or less equal masses, not a planetary case, but a general problem. And well, it is. Well, he was asking questions like, if you have this situation here, does it exist? Does it exist any open solution at all? There was an opinion of Poincaré. We don't really know where it goes at all, but this is kind of random situation. It might go this way today and that way tomorrow. Sundman actually developed a series where you can calculate a small bit definitely. So there's kind of mathematical proof that you have a definite orbit. But it's just a mathematical proof. You could never calculate by this method. In fact, I think somebody's estimated if you want to calculate this kind of whole orbit, I think you need something like 10 to the power 120 terms from this series. So it's much faster to use a computer to calculate the orbit. So nobody has ever tested this theory because it's just
Not even that was before the computer.
yeah, well,
There was no help from the computer.
yes, no, nobody has ever calculated any orbits using this method. It's just the series converges so slowly, and you're not sure if it does actually. Well, I'm quite sure it doesn't generally, so in case it doesn't even. But it's a mathematical proof that something exists. Typical mathematical stuff.
I have one question. Did the cosine mechanism have to await the introduction of computers for its discovery, or could Poincaré have actually?
No, of course, I didn't have computers to use. 1962, people didn't really calculate all this. I think it was analytical.
And the assumption of point masses for the bodies, does that have any implications if you use a finite size solar body?
Yeah, it does. In fact, that if the deformation from it's not a spherical body, but the long body, then that would cause some precession as well, and that would destroy your cosine mechanism. But it's like in a solar system, it works all right. Some close binary systems, it probably does not work at all.
Have you thought of rerunning these computations on extrasolar planetary systems where the extrasolar planets are found in binaries like say Epsilon every time?
Yeah, I know I haven't thought of it, but it's easy to do. Well, I think what you've been talking about is something like
Alright, we have to move on. So, and